Hi, here we are. For what? For our physics class. Okay? We have started thermodynamics. One chapter is over in thermodynamics. The next chapter we are going to start today. Okay? Isothermal and adiabatic process. It's some certain points you know already about isothermal, adiabatic, etc. We are going to study in a detailed manner today. Okay? So just see today's objectives: isothermal process, adiabatic process, and work done during isothermal and work done during adiabatic process. Okay? Here derivations are there for this work done, right? These are our objectives. Since it is isothermal, adiabatic, and those terms are not new for you. Why? Last class you have studied the same. Recall what all terms we have studied in the last class. Thermodynamics introduced. Then zeroth law. Terms in that: heat, work, internal energy, all those things. Importance of indicator diagram, first law of thermodynamics and their applications. Okay, all those we have studied, right? Okay, fine. So now as it is seen in your learning objectives, isothermal process, adiabatic process, then derivations of their work done. First topic itself, let us take isothermal process. What is isothermal process said? Isothermal, yes, temperature same, process in which temperature is same. In order to conduct an isothermal process, temperature should be maintained same. That is, when a thermodynamic system considering, when the process is thermodynamic process is taking place, temperature should be maintained same. Therefore, the system or the gas is taken in a container with conducting walls. Bottom and sides will be conducting. Because of that, when the gas is expanded, actually when it is expanding, expansion is a cooling process. But when it is expanding, it is absorbing temperature from the surroundings because it is conducting walls, thus maintaining the temperature of the gas same. Then when it is getting compressed, since it is conducting walls, the amount of heat energy developed inside will be radiating outside and maintaining the temperature same, right? Thus, if the temperature of the system is maintaining throughout, it can be called as isothermal process. Okay, it's a PV diagram also we have seen. So let us see isothermal and adiabatic process at a glance once again. See, isn't it clear now? Perfect conductor. Therefore, when the piston is moving slowly up and down, it is absorbing or evolving temperature, radiating temperature to the outside or the surroundings, temperature is maintained same. That is, equation for isothermal process is PV equal to constant, Boyle's law. Pressure into volume will be constant. Okay, it's a graph also you can see, PV diagram, indicator diagram, isn't it? Can see the slope, right? For an isothermal process, PV diagram, indicator diagram is here, slope also mentioned. See the case of adiabatic process. Did you understand now what is adiabatic? What is adiabatic? Temperature is varying. Process in which temperature is varying. See how do the system is taken? It is perfectly insulated. Because of that, no heat transference is taking place with the surroundings. Therefore, when the gas is expanded, it will be cooled, temperature reduced. When the gas is compressed, temperature will be increased. Thus, the process in which the temperature change is occurring, it is called adiabatic process. Okay, adiabatic process. So, its indicator diagram you can see its slope will be greater than the slope of isothermal process. And the equation we are representing is PV raised to gamma, something new to you. PV raised to gamma is a constant. Okay. When we are applying gas equation PV equal to RT, instead of P, if we are substituting the value of RT by V, it will be then T V raised to gamma minus 1 is constant. Okay. Then instead of V, if we are substituting in terms of RT by V, it will be T raised to gamma by P raised to gamma minus 1 will be constant. Okay. So, adiabatic process means temperature is maintained, temperature is varying. Isothermal means temperature is maintained same. Okay, equations also, PV diagram as well as equations are important. Isothermal means Boyle's law, PV equal to constant. Adiabatic means if it is adiabatic process, since the temperature is changing, PV raised to gamma is a constant. Okay. In order to understand gamma easily, gamma is nothing but, you have studied about specific heat capacities. Okay. Specific heat capacities. The ratio of two specific heat capacities. Specific heat capacity of the gas at constant pressure to constant volume is known as gamma, and usually we are using its value, that's equal to 1.4. At normal temperature and pressure, it's equal to 1.4. So, PV raised to gamma is a constant is for adiabatic. By using the gas equation of PV equal to RT, PV can take as RT by V. By substituting this, we will be getting TV raised to gamma minus 1 constant. Instead of volume, if we are substituting volume as RT divided by P, we will be getting T raised to gamma by P raised to gamma minus 1 constant. Likewise, for adiabatic and isothermal process, various equations are there. These equations to be by hearted. Okay, we have seen just now equations and what is meant by this also to be. Therefore, I said gamma is equal to Cp by Cv. Gamma is also having one more meaning. See this diagram now. When we are taking the isothermal curve and adiabatic curve, as you can see, first one is for their expansion, second one is for their compression. Volume change you can see. So, for isothermal expansion or isothermal compression, adiabatic expansion and adiabatic compression, when we are plotting their indicator diagram together, expansion of both together and contraction of both together, you can see the change in their slope. In both the cases, slope of adiabatic curve divided by slope of isothermal curve's value will be equal to Cp by Cv, which is equal to gamma. Okay. So, gamma is either Cp by Cv, specific heat capacity at constant pressure to constant volume, or slope of these curves, adiabatic to isothermal curve. Okay. So, about gamma it's clear, gamma is a constant, easy to remember, its value is 1.4. Okay. Cp by Cv it's equal to 1.4. So, isothermal temperature is constant, adiabatic temperature is varying. Isothermal PV equal to constant, adiabatic PV raised to gamma is constant. Okay. For doing the numericals and all, next all versions, next all forms of these equations we have to see, studied. Okay. Next important one is have to derive derivation of work done during isothermal expansion and compression as well as adiabatic expansion and compression. Let us see some integration also we are using. So, let us start. Okay. For isothermal process, always in order to explain isothermal process, the container will be having conducting walls and bottom. For what? In order to maintain the temperature as constant. So, here for our derivation, we are taking 1 mole of gas. Okay. For 1 mole of gas, we are deriving the equation at last. So, 1 mole of ideal gas is taken. Okay. And it is undergoing isothermal expansion, changing its volume from V1 to V2. It is undergoing expansion isothermally, maintaining temperature as same. Then how much is the work done for that? That is what we have to calculate. In thermodynamics, work done is calculated by the formula P dV. That also should be there. Okay. Work done is calculated as P dV. So here, in order to expand isothermally, work done is equal to small work done means P into small change in volume. In order to calculate the total work done means integral V1 to V2 P dV, starting to ending P dV. Okay, integral V1 to V2 P dV. Then here volume is the changing factor, but here P is there. So next step, P we have to convert in the form of volume. For that ideal gas equation we can depend. Ideal gas equation is equal to PV is equal to nRT or mu RT. Mu or N we can use, number of moles. So PV is equal to mu RT. For 1 mole we can take it as 1, that we can do at last. According to this equation, PV is equal to mu RT. P we can take as mu RT by V and can substitute this value of P there. Therefore, integral will be, work done will be equal to integral V1 to V2 instead of P mu RT by V dV. Okay, instead of P value we are substituting, right? Then we can do the integration. As you can see, mu RT, constant temperature also, R, universal gas constant. So all these are constants. Therefore, we can take mu RT outside the bracket, outside the integral sign. Then integral V1 to V2 1 by V dV. Okay, integral V1 to V2 1 by V dV. What is integral 1 by V dV? Log V, log to the base E V. Okay, log V, 1 by V dV means log V. So here we can write mu R T, integral 1 by V dV is log to the base E V. Log V between the limits V1 to V2. Clear? Applying the upper limit and lower limit, what is the format? Upper minus lower, upper limit minus lower limit. So it will be mu RT into log to the base E V2 minus log to the base E V1. Okay, what is log A minus log B? Log A by B. Therefore, here mu RT log to the base E V2 minus log to the base E V1 can be written as, work done can be written as mu RT log to the base E V2 minus V1 means V2 by V1. Okay, log to the base E V2 by V1. This is isothermal process. What's the equation for isothermal process? PV is equal to constant, or product of pressure and volume is constant. Here volume is changing, pressure is changing. So we can write P1 V1 is equal to P2 V2. Okay, P1 V1 is equal to P2 V2. So instead of V2 by V1, we can write P1 by P2 also. Okay, instead of V2 by V1, we can substitute in terms of pressure also. By substituting, so what will be the equation? Mu RT log to the base E V2 by V1 can be written as P1 by P2. Okay, both are different forms of same equation, that is work done for isothermal expansion. Okay, then since it is natural log to the base E, natural one, we have to convert it into arithmetic one. Okay, so as base 2 we have to do. In order to convert that, we will be multiplying with 2.303, so it will be 2.303 into mu RT log to the base E will be, log to the base 10 then. Okay, natural log is changing into arithmetic log. Then it will be P2 by V1. Okay, or in terms of pressure means 2.303 mu RT log to the base 10 P1 by P2. So all these are the expressions for isothermal expansion. Okay, if we are applying, taking in the opposite manner, while putting a negative sign, it can convert into compression also, right? Isothermal expansion, right? See the steps once again. Work done during isothermal expansion, work means PdV. Total work means integral of PdV. Since the volume is changing from V1 to V2, we are writing V1 to V2 integral PdV. Then P we are substituting according to gas equation mu RT. So mu RT by V dV. After that we are integrating according to the formula of integration, 1 by V dV is equal to log V. So it will be log V within the limit V1 to V2. But after applying the limit, it will be log V2 minus log V1. But log A minus log B is log A by B. According to that, the next step, mu RT log to the base E V2 by V1. According to isothermal equation, PV is equal to constant. We can write V2 by V1 as P1 by P2. So, in terms of pressure, we can write mu RT log to the base E P1 by P2. While converting natural log into arithmetic log, I have to multiply 2.3026 or 2.303. By multiplying, as you can see here, we will be getting the formulas. Clear? This is for isothermal expansion. Now, if we are choosing the same isothermal compression, see the equations. What change is there? Compression means direction is opposite. Instead of moving upward, it is moving downward. So, all the equation becomes negative. First equation negative. That negative while taking inside, V2 by V1 becomes V1 by V2. Okay? Okay? PV is equal to RT. So, instead of when we are using after applying and all, we are getting RT V2 by V1 or P1 by P2. While taking the negative sign inside, P1 by P2 becomes P2 by P1. Okay, and you can see one J RT divided by J. That J is mechanical equivalent of heat. That is, W is work. When converting into heat energy, that conversion factor is called J. Okay, J is equal to, you have studied, no, 1 calorie is equal to 4.2 joules, the same thing. Here J is called mechanical equivalent of heat. Okay, mechanical equivalent of heat. In order to convert work to heat, we can divide with that constant J called mechanical equivalent of heat. Okay, so work done during isothermal expansion, then compression also. We extended the result for compression also. Is it clear? All the steps? Okay. Shall we move on to the next one? Yes. Next is work done during adiabatic expansion. Right? Adiabatic process, what we said? For adiabatic process, completely it will be insulated. An insulated system or isolated system. What is isolated system? There is no interaction is there with the surroundings. Okay. So, for adiabatic process, complete the walls and the sides of the container is insulated. Because of that, when it is expanding or it is compressing, temperature change will be there. Not like isothermal, opposite of isothermal. Such a process is adiabatic process. So, here also we have to see what is the work done. Okay, methods are same, but the equation will be differently have to be substituted. It is specifically for adiabatic one. So, adiabatic equations to be used. Shall we start? Okay, here also work done can be calculated as total work done. Therefore, volume is changing from V1 to V2. While taking PdV, we can take integral V1 to V2 PdV. Okay, integral V1 to V2 PdV. Right? Now here, when we are substituting the equation, our equation is PV raised to gamma is a constant. Here this constant we can name it as for a name. In order to apply it in the equation, let it be K. PV raised to gamma is a constant. Constant is represented by K here. Okay. Therefore, P we can substitute as K divided by V raised to gamma. K divided by V raised to gamma. Since V raised to gamma is in the denominator, while taking it into the numerator, it can be written as KV raised to minus gamma. Negative sign is indicating it is in the denominator. So, KV raised to minus gamma. The same thing we can substitute here. Work done is equal to integral V1 to V2. P is equal to K V raised to minus gamma into dV. Okay, K V raised to minus gamma into dV. What is integral x raised to minus 1? Okay, or integral x raised to minus n. X raised to minus n is minus n plus 1 divided by minus n plus 1, isn't it? Okay, plus 1. It's just opposite of derivation. So, integral x raised to n is x raised to n plus 1 divided by n plus 1. Here n is minus gamma. So, minus gamma plus 1 divided by minus gamma plus 1. So, when we are applying the formula of integration here, it can be written as work done is equal to integral becomes K can be take outside minus gamma plus 1 divided by minus gamma plus 1. Okay. So, it can be written as 1 minus gamma in both the places. V raised to 1 minus gamma by 1 minus gamma within the limit V1 to V2. Okay. V1 raised to 1 minus, V raised to 1 minus gamma within the limit V1 to V2. Now, normally what we are doing, we can apply upper limit. First upper limit, then lower limit. So, it will be K into 1 by gamma also we can take outside. So, K divided by 1 minus gamma into V2 raised to 1 minus gamma minus V1 raised to 1 minus gamma. Again, some modifications we are going to do to get our convenient format to express V2 1 minus gamma minus V1 1 minus gamma. Okay. Then, what is the value of gamma? 1.4, greater than 1. Therefore, it is better to write gamma minus 1 format. Okay. So, everywhere we are going to change gamma minus 1. So, one negative sign is coming. According to that, gamma minus 1 here also gamma minus 1. So, minus becomes positive. Likewise, while modifying, we can write the equation as K divided by gamma minus 1 into V1 raised to gamma minus 1 minus V2 raised to gamma minus 1. Okay, minus V2 raised to one minus is coming here, one minus is coming here. So, it will be altered, but here one minus is there, therefore inside again it will be coming in the denominator. Here one minus is there, here one minus, here also one minus. So, slowly one by one, step by step while taking we can see K divided by gamma minus 1 into K divided by V1 raised to gamma minus 1 minus K divided by, since K is outside, 1 divided by V2 raised to gamma minus 1. Okay. Again, instead of K, we have here V1 raised to gamma is is equal to P2 V2 raised to gamma is equal to a constant, okay, for adiabatic process. Therefore, instead of K, if we are using this, instead of K, while taking K inside, it can be 1 divided by gamma minus 1 and K we can take inside. Then by substituting the value of K as P1 V1 raised to gamma here, P2 V2 raised to gamma here, okay, instead of K, P1 V1 raised to gamma, P2 V2 raised to gamma. According to adiabatic process equation, constant can be PV raised to gamma. So, taking. Now, when V1 raised to gamma minus 1 while taking to the numerator, V1 raised to minus gamma plus 1. So, minus gamma is here, plus gamma is there, cancels. While taking it to the numerator, it will be then 1 by gamma minus 1, gamma and gamma cancels. Then what is there? V1 only. V1 raised to plus 1 is getting P1 V1. Similarly, other side also P2 V2. Okay, P1 V1 minus P2 V2. No doubt there, no? P1 V1 raised to gamma. When we are taking V1 raised to gamma minus 1 to the numerator, it will be V1 raised to minus gamma plus 1. So, plus gamma minus gamma cancels, V1 raised to 1 is remaining, that is written as V1 alone. Okay, so P1 V1 minus P2 V2 is the equation for adiabatic expansion. Instead of P1 V1, according to gas equation, PV is equal to RT. Since temperature is changing, P1 V1 can be RT1, P2 V2 can be RT2. That manner also we can write R, since R is common, we can write P1 V1 is equal to RT1, P2 V2 is equal to RT2. So, while replacing, we can write 1 by R by gamma minus 1 T1 minus T2. Okay, T1 minus T2. Here, for 1 mole we are considering if for any value mu RT to be used, like last time we were using. If mu equal to 1, directly we can write T1 minus T2, R by gamma minus 1, T1 minus T2, right? Okay, go through the steps once again from the beginning as we were doing. First PdV, then PV raised to gamma is equal to constant, then integrating V raised to x is equal to, or x raised to n is equal to x raised to n plus 1 divided by n plus 1, substituting, we will be getting V raised to 1 minus gamma by 1 minus gamma. Applying the limits V2 and V1. After applying the limit and taking the value of K as P1 V1 raised to gamma, we are getting it as P1 V1 raised to gamma by V1 raised to gamma minus 1 minus P2 V2 raised to gamma by V2 raised to gamma minus 1, and outside the bracket 1 by gamma minus 1. After solving and all, we will be getting 1 by gamma minus 1 into P1 V1 minus P2 V2. Or for 1 mole of gas, it is mu R gamma minus 1 T1 minus T2 becomes mu is equal to 1, then R by gamma minus 1 T1 minus T2. Okay. The same thing if we are using for compression, negative sign to be used. Like isothermal, what we were doing here. Negative R by gamma minus 1 T1 minus T2. R by gamma minus 1, negative is taking inside, it will be T2 minus T1. While converting into H, it can be R divided by J can, but R as well as J constant, altogether we can say the constant R itself by gamma minus 1 into T1 minus T2 or T2 minus T1 as it is there, T2 minus T1. Okay. J is there, but that J is along with R, it is considered. The value will be R by J then. Okay, magnitude will be that then. Okay. Okay, so this is about work done during adiabatic compression. Okay, yeah, that's all for today. It's derivation, right? So we have seen what is isothermal, their derivation, adiabatic's derivation. So steps are same. First equation, respective equation, work done is equal to PdV. Integrated, applied the equation of isothermal's case, isothermal, and adiabatic's case, adiabatic's equation. Okay, and we modified the result. For compression, negative sign we had given. Okay, with that everything is completed. Right. So just recap what all things we have completed today. Isothermal process, its equation. Adiabatic process, its equation. Their gamma also we have seen. Then work done's derivation for isothermal process and adiabatic process. Okay. Since it is derivation, in the worksheet also the same derivation is asked. So you have to derive it with the help of that simple, or even though the diagram is simple, small diagram, you have to draw the diagram when you are deriving it. So with the help of diagram you have to derive it, and thus want to complete the worksheets attached here. Okay. Okay, then shall we conclude? Okay, thank you all. Complete by studying this portions given here. Once again, bye bye.